for today, and by the way, this here, don't worry about right now. Okay, this is going to come back into play later. I just wanted to have it written, but you don't have to have this written. So we're going to do division of polynomials and the remainder and factor theorems. So our objectives: divide polynomials using long division. Next objective: divide polynomials using synthetic division. And then the last one: apply the remainder and factor theorems. Okay, so there's a lot going on with the last objective, but the first two is just kind of refreshing our minds with, how do you use long division with polynomials and how do you use synthetic division. Okay. So let's go ahead and start dividing. This is going to feel weird. I'm not starting off with a definition. I'm starting off with an example. Use long division to divide. There we go. So just like normal long division, let's draw the division bar there. And let's put the divisor and dividend where they need to be, right? So this is our divisor. Dividend is what's going to be underneath here. Now, a couple things. When you're doing this, you want to keep track of two things. The first thing you want to keep track of is, are the powers written in descending order? Okay, and this is, right? So we're good. If they're not written in descending order, make sure they are, okay? Because that's going to mess up your division. The second thing that I want you to keep track of is, are there any terms missing? So what I mean by that is, look at your descending powers. Is there a power missing as you're going down the rank? I think there is one, huh? This does not have an x squared. So what we're going to do to make it everything nice and vertically aligned is I'm going to put a 0 as a placeholder there, okay, for an x squared term. Because if you don't do that, well, when you start dividing, terms are going to be mixed up. It's not going to work out too nicely, so the 0 is a good way to keep things vertically aligned, okay? So we're going to have 6x to the 4th plus 7x cubed. It doesn't matter if you put plus or minus, because it's just 0. So we'll just put plus 0x squared minus 13x minus 2. So let me use green. So very important, missing x squared term. Okay? And that's easy to miss. Like when you start dividing things, that's something that maybe not jumps to like the forefront of your brain, like, oh, I need to put a 0 there. Now, just like normal division, let's start it out. Can two terms go into one term? Absolutely not, right? But two terms can go to two terms. Now, when you divide with long division, the easiest way to approach it, just look at the first term for right now, okay? What can I multiply this 2x by to get a 6x to the 4th underneath it?
3x to the 3rd.
Very good. Said that in unison. That was scary. Okay. So yeah, 3x to the 3rd. So that's what I would do. Because if you're looking at this, there's a lot going on. So it's easier just to look at the first term. How do you eliminate it? What do you multiply this by? Okay. Now you're going to multiply this to both of these and put it right underneath here. So 3x cubed times 2x, we already know is 6x to the 4th. That will help us eliminate it. 3x cubed times 1 is just 3x cubed. Okay? First term, gone. Second term, 7 minus 3, that's a 4. 4x cubed. Bring down the next term. So we're going to bring down a 0x squared, okay? Sounds weird, but again, it's going to help us vertically align this to where the x cubed terms are together, the x squared terms, the x's, and so forth. Now, rinse and repeat. What can I multiply this by, the 2x, to get a 4x cubed underneath here?
2x squared.
Yep, 2x squared, right? Again, just focus on the first term. Okay, it makes it easier. Now we multiply. So 2x squared times both of these terms. So I get a 4x cubed, which is what we wanted. 2x squared times 1 plus 2x squared. So we get a 0 And the other one would be what? Minus 2x squared. Okay? Bring down the next term. I would recommend as you're doing this, make sure you're writing neatly, because you can see where some issues could happen if you do this kind of sloppily. Okay, what can I multiply this by to get a negative 2x squared?
X.
Yep. Not just an x, but a negative x, right? So we get a negative 2x squared, and then we get a minus x. So again, you want to match that term. So to match the term, it has to be another negative 2x squared. Because when we subtract it, that becomes positive, it cancels out. Okay, negative 13x minus a negative x, so we're adding, so this will be minus a 12x. And the last one, we're just about there. Now, I gotta multiply this by something to get a negative 12x there. So what would that be? Minus 6, right? Yeah, negative 6. Very good. Again, take the negative 6, multiply to both of these. So that would give me a negative 12x, and a negative 6 times the 1, minus 6. So 12x's are gone, negative 12x's. And then we get negative 2 minus a negative 6, so it's like we're adding, well, we got 4. And just from normal division, we know that's going to be our remainder, which can happen, okay? Sometimes we don't have a remainder, sometimes we do. So let's just go ahead and write down, let's review some basic division words. It's good to remind ourselves, because a lot of times we go so far in mathematics we forget some of the basics. It happens. So here we go. So the quotient of this problem, okay, that's what our answer is. So 3x cubed plus 2x squared minus x minus 6. Okay. The remainder, well, we know what that is, I just told us. That's the number that's left. So that's the negative, or no, not negative 4, positive 4. Next, the divisor. Okay, so that's what we're dividing by, so that's 2x plus 1. And then what are we dividing? We call that the dividend. Okay, did I spell that right? Yeah. And that's going to be the 6x to the 4th plus 7x cubed minus 13x minus 2. I'm not going to include the 0 term because, again, it's just there to help us to divide. It wasn't the original. Okay? Pretty cool, huh? Now, let's talk about the division algorithm. Okay, so now that we have this, let's use this to explain a couple things. Suppose that f of x and d of x are polynomials where d of x doesn't equal 0 and the degree of d of x is less than or equal to the degree of f of x. Then there exists unique polynomials q of x and r of x such that f of x equals d of x times q of x plus r of x. Okay? Now this is something that we instinctively do when we divide anyway. It just doesn't look like it because we get all those math terms in it, huh? It can sound a little bit confusing. Okay? So let's think about something for a minute. What is this telling me? Okay? Well, let's use the information from the prior example to fill it into here to make it a little bit easier to interpret. So think about what we're dividing by, okay? So we're dividing, well, not what we're dividing into, my apologies. It's the 6x to the 4th, 7x cubed, 0x squared minus 13x minus 2, okay? So let me write this down here. And let me make sure, I want to make sure I'm taking my thunder away from a different example, because that would be bad. No, I'm good, okay. Making sure. Okay, so let me put in 6x to the 4th plus 7x cubed minus 13x minus 2. Okay. So my divisor, what am I divided by, is 2x plus 1. Okay. What's my answer? My quotient is going to be the 3x cubed plus 2x squared minus x minus 6. I just had enough space. And then r of x is my remainder, which is 4. Okay? So here's what the division algorithm is telling us. What I started with was this guy. Okay? So if I take what I'm dividing by, multiply it by my answer, add my remainder, I get this. I get the original. Okay? That's all this is telling me right here with what I just did over there. Now, a lot of times, that still might not click. So let's just put a normal number example down there. Okay? So let me do something like this. Let's do 9. Okay, so 9 is equal to 4 times 2 plus 1. So if I were to divide 9 by 4, okay, I could multiply it by 2, and my remainder is 1. So here's a nice number example that kind of exhibits what this is doing here. Okay? Any questions on that? That make sense? Yeah. The only reason why we have function notation is because, well, those are functions, right? So even the 4 is a function, because think about it as a vertical line test. It will support it. All right. Moving on. So we have here, use long division to divide. I want to do one more long division problem. That problem, we had a missing value here, okay? So we had a missing value in our dividend. Now I'm going to put a missing value here in our divisor and see how that works with it. It kind of is the same thing. You're going to put a 0 as a placeholder. But it's good just to have an example to reference from. So here we go. We got negative 9 minus 13x minus 6x cubed plus x to the 4th minus x squared divided by x squared plus 3. Now, a couple things with this problem. First, this is scrambled big time, okay? It's not written in any order. So when I write this in my long division problem, I want to make sure I start with the largest, which is x to the 4th, and work my way down. Over here, what I'm dividing by, there's no x term. So because of that, I'm going to put a 0 as a placeholder. So right in here, I'm going to put no x term, okay, as an alert, like, hey, I got to put a 0 there. For this polynomial, every value is here. So I got 4, 3, 2, 1, and a constant. I don't have to put no zeros. And yes, if there's no constant, you still have to put a 0 as a placeholder. Okay, that's very important. So let me set this up. So x squared plus 0x plus 3. And I'm going to write this in descending order. Okay, just like that. So now we have an example where there's a 0 here as a placeholder. Okay, the process isn't going to change. We're still going to go through the same steps. I got 3 terms here. I can't put into 1 term. I got 3 terms. Can't put into 2. So 3 into 3, we're good. I want to eliminate the first one. So what can I multiply an x squared by to get an x to the 4th under here? Well, that's an x squared, right? Now I'm going to multiply this to all 3 of these. So I get x to the 4th. Okay, it'd be a plus, well, 0x to the 3rd, but that's okay. Again, it's there to help us to keep things lined. And then the last part would be a plus 3x squared. Okay, so this is gone. This will just continue as a negative 6x cubed. And then over here, negative minus a 3, so that's going to be minus a 4x squared. Okay. Bring down the negative 13. Rinse and repeat. So again, I want to multiply this by some number to give me a negative 6 cubed underneath it. So that's going to be a minus 6x. That's what will do it for me. So negative 6x times all three of these. So negative 6x cubed minus, well, maybe a 0x squared. Again, that's okay. It's just good to have a placeholder. And then the last one's going to be minus 18x. Just like before, just like we want, these cancel. Negative 4 minus is, well, negative 0, doesn't matter. It's still going to remain as negative 4x squared. Negative 13 minus a negative 18 makes it a positive, so it'll be a plus 5x. Now, before I finish this problem, I want you to think about something. There's a lot of negatives going on here, right? You see how it's easy to make a mistake? So, is there another method, yeah, that is a little smoother to where we can solve this without the negative errors? And the answer is yeah, we're going to use synthetic division as a way to make this process a little simpler. So anyway, with a negative 9 down, and then I think that's going to be what, a negative 4 to finish it? So I have negative 4x squared. Again, to be a 0x. Doesn't matter if you put plus or minus, it's just 0. And then minus 12. So the first term cancels. This will just give me a 5x. And then negative 9 minus a negative 12, so that would be what, a plus 3. So this has a remainder, which isn't a bad thing. Okay? Now, how do I write my answer? Because that's something I didn't do in the first example. So how would I write this formally? Okay. So my answer would be x squared minus 6x minus 4. Okay, that's what our answer is up there. And then for the remainder, we typically write a remainder as the 5x plus 3, and then what we divided by, which is the x squared plus 3. So this last part is how we write our remainder, which is just what you did with normal long division with normal numbers. We're just following the same pattern to it. Okay. All right. Questions? Now you can check your answer. In other words, if I were to plug these values into our division algorithm, I can multiply this times this, and I should get the original underneath it. Okay, and I do. Just to save a little bit of time, I just want to make sure I verify that, yes, you can do that. Just like down here, right? If this was my division problem, I could still multiply and add the remainders to check to see that it does equal what it should be at the original. Okay, let's talk about synthetic division. Now, one thing to note with synthetic division, okay? The process of synthetic division works if the divisor is a binomial in the form x minus c, and c is a constant. Okay, it's the only time that this is going to work. If you don't have something you're dividing by, which is x minus a number, or even x plus a number, that's okay. We'll talk about what that looks like. Then you're good to go. But over here, well, it's not written like that, right? So I couldn't quite use synthetic division, even though it would have been nice. Would have got rid of a lot of negatives that we have in here. Okay, let me go ahead. I'm going to jump into an example of how to do synthetic division. And then, on this whiteboard, I had a long division problem for us. We're going to make comparisons to see why does this work, okay? Because it's pretty crafty. use synthetic division to divide. There's my problem. Now, a couple of red flags. The first red flag, this is not written in any order, right? So immediately I want to write it in descending order. So that's on my mind, okay? The second thing, I don't have an x cubed term in here. My largest power is 4, but if I go in decreasing order, the cube should be next, and there isn't. So automatically I'm going to have to put a 0 in place for that. So let me just put that underneath as a reminder. So we have no x cubed term. Okay, that's a big red flag, so we've got to make sure we keep that in the back of our heads. So here's how you use synthetic division, okay? It's like the division you see over there, but we're flipping it upside down. Now, what I'm dividing by, this guy, I'm not worried about the x, okay? I'm only worried about the constant. And what I have to do is take the opposite of this. So if it's a positive 2, I'm going to make it a negative 2. Again, I'll explain a little bit more afterwards why that's the case. Same thing, I'm not worried about the variable. Because in the end, look at what we have over here. These variables always are going to line up, right? You're always going to have x cubed over x cubed, x fourth over x fourth, and so forth. So I'm just worried about the coefficients. That's where the action is. So starting in descending order, I'm going to write all the coefficients. So my largest one is x to the 4th. So what's in front of it? A 2, okay? Now I don't have an x cubed term, so I got to put a 0 as a placeholder. Next would be negative 11. Next would be negative 9. And then my last, which is the constant, that's negative 10. So when you're doing synthetic division, there's a lot to keep track of and set up. But once you have it set up, the rest of the process is really slick. You always carry down your first term, okay, that never changes. And then what I like to do is I like to put plus signs here because we're going to be adding things. So to me, that helps remind you that you're going to be adding, okay? If you see textbooks and other places, like they don't put the addition signs there. I like it just because it helps. Now, how does this work? You take what you're dividing by, multiply it by the bottom number. That's a negative 4. That answer goes right in this spot, okay? Then you add the column. So this becomes a negative 4. Repeat the process. Now, the negative 2 gets multiplied to the negative 4. The answer goes in this spot. So that's going to give me a positive 8. Add the column, you get a negative 3. See where it's going? So then again, we just erase it. I won't do this every time, just first time doing it. Multiply these two together, answer goes in this spot. So that's going to be a positive 6. Then we get negative 3 when you add the column. And then our final step, okay, we're going to take the negative 2 times the negative 3. Okay, we get another positive 6. And that gives me a negative 4 in the end. Okay. All right. Now you're probably thinking, great. What's the answer? We just got a bunch of numbers down here, right? Well, I want you to think about something. Over here, okay, we start with an x to the 4th, right? We're dividing an x squared into it. So we're losing 2 powers. So the answer is going to have 2 powers less, okay? Over here, and because I'm recording a video, I better make sure that the video can see it. I'm dividing this by just an x, right? X plus 2, but just an x. So it's going to be 1 degree less than what you start with, which is to the 3rd, okay? So it just depends on what you're dividing by. So in this example, my largest power is a 4, and I'm dividing by an x, so it's going to be 1 less. So that means the first spot is an x cubed spot, okay? So this is going to be 2x cubed. Then you go in decreasing order. minus 4x squared minus 3x minus 3. Now your last number is the remainder. So we're going to write our remainder just like we did over there. So this is going to be plus 4 over, what was it, x plus 2? Yeah, x plus 2. So there's my final answer using synthetic division. Okay? It's great, right? Yes?
Would it be a
Negative 4? Ooh, thank you. Appreciate that. It's a very cool process. It's simpler, right? It's faster. There's a lot to make sure you remember how to do it, though, right? That's the only downside. Now, why does this work? Glad you asked that. This was the problem I wrote in the beginning. I said, don't write it. That's this problem using normal long division. Okay, so let's make some comparisons just to see. Notice that every single one of these, just like I said before, the first term is always canceling out, right? No matter what. So I don't have to worry about that. I know it's guaranteed. What comes after it, well, that's this guy, right? That's what's deciding what's happening next, the second term, okay? Hence why I only focused on that number. Now, why do we take the opposite? Well, what's easier to do, subtraction or addition? Addition, right? So by taking the opposite of this, I don't have to subtract each time. I could just add. So I'm taking a negative out of everything. So it makes it a lot easier then. Okay? So again, I'm not worried about the first terms because they're always going to cancel out. It's just the second terms I'm worried about. That's what this is doing at the very top. So when we're getting our final answer, we're only getting the coefficients because, again, the x's are always going to be paired up nicely. And then at the very end, we can include the x terms that we just nixed at the very beginning. So yeah, that's pretty cool. I mean, put it this way, when I was doing long division myself, I mean, this isn't what came to mind, right? That's not something I thought of. So it is a awesome little tool when it comes down to it. Okay, moving on. Let's see where we have. Okay, so this leads to our last objective. We're going to talk about the remainder and factor theorems. Okay, so now that we have a little bit of division under our belt, how can we use this to find like zeros or to factor polynomials? Because that's important. Because this is all fine and dandy, but it needs to have a reason. Like, why do we divide these things? So with the remainder theorem. So let's look at a special case of the division algorithm. The thing I just erased. Wish I would have kept it up here. Oh well. Where f of x is the dividend and x minus c is the divisor. So what we're dividing by. Okay? So we write this underneath it. So it's going to be f of x equals x minus c times q of x plus r. So again, it's just like the normal division algorithm I had before. Instead of me putting, I think I had a d of x here originally. So this is just like the x, oh, this got erased. That's like the x plus 2. So x plus 2 times what plus the remainder gives me what I had originally. So let's do this. Let's sub c into f of x. So in other words, if you look at the prior example, let's say I just subbed 2 into it, right? Or in this case, a negative 2, because it has to be the opposite there. Okay, so what's going to happen? It's going to change some things up. Okay, so if I plug c into it, oops, no, we're good. So if I plug c in for x, you can notice that the first term is going to turn to 0, huh? C minus c is 0. So this gives me 0 times q of c plus r. And, well, 0 times anything is still 0, so you just get r, which is our remainder. Okay? So what did I do? Let me just recap. So I took something like this, okay, and I said, well, let's just plug a -2 into here and see what happens. Well, everything kind of gets taken out. The only thing that's going to remain is our remainder here. So in other words, what we discovered is this. If I want to plug a -2 into here and see what the answer is going to be, our answer is going to be the -4 here, okay? So instead of me actually plugging in -2 in the whole function, okay, I can use synthetic division to get to that answer faster. So let's just put an example next to it. That way it's a little bit more clear. So let's try a problem now. And we are going to use synthetic division, okay? Make it a little bit easier. So let me tack this on at the very end, and then we'll do the example. So if a polynomial, one final note with this, f of x is divided by x minus c, then the remainder is f of c. So we're going to see that in this next example. Given that f of x equals x cubed minus 2x squared plus 7x minus 6, use the remainder theorem to evaluate f of 1. And again, we're going to use synthetic division to make it easier. Now, could I figure this out without division? Yes. Okay. All it wants you to do is what? Plug 1 into here and get an answer. But looking at what I talked about with the remainder theorem, I can get to the answer the same way as if I just divided this by 1. Okay? And whatever the remainder is will be the answer. So let's set up our division problem. Just put this underneath it. Okay? So what we're dividing by is a 1. So we're going to put a 1 there. And then again, you have to be careful. If there's any missing terms, you got to put a 0. And there isn't. And everything is in descending order. So this is perfect. So this would be a 1, a -2, a 7, and a -6. Always bring down the first term. That doesn't change. Okay, put plus signs over here. And let's go through the process. So we'll do 1 times 1, which is 1. Add the column. I get -1. 1 times -1 is -1. Add the column. I get 6. Then 1 times 6 is 6. Add the column. I get 0. Right here. That's my answer. So f of 1 is 0. But let's do some convincing here. Let's actually plug 1 in and see if it gets 0, okay? So let's see if it works. If I plug 1 in, I get 1 cubed minus 2 times 1 squared plus 7 times 1 minus 6, okay? So let's see. This will be 1 minus 2 plus 7 minus 6. So 1 minus 2 is a -1. Plus 7 is a 6, minus 6 is indeed, hey, it's 0. Well, yeah, no, not yeah, yay. There we go. That was like a sarcastic thing. Yeah, of course. But yeah, there we go. So using a little bit of division, we can actually evaluate a function. Okay, now, put it this way, it was probably more work to do that than to plug it in, right? If there's functions that are longer, more complicated, it might be easier to plug something into here than to plug the number in. But it's just a nice little cool fact, okay? Any questions so far? Let's keep going. So that's the remainder theorem. Another little tool that we can use for anything in the future. Let's talk about imaginaries. A polynomial whose coefficients are complex numbers is called, wait for it, complex polynomial. Now, I'm going to show you how to divide with something like this. That's pretty much as far as we're going to go in terms of complex stuff, okay? We're not going to worry too much about dividing like a complex number into a complex number and stuff like that. We kind of did that already, multiply with a conjugate for that to work. But for this case, I'm going to teach you how to do it using synthetic division, okay? So just real quick, so going back to division, a complex number, which we'll say is a plus bi, okay, is a 0 of a polynomial f of x if f of a plus bi equals 0. Okay, so for example, f of x equals x minus the complex number 5 plus 2i. Okay, so if I were to solve that, okay, like set this equal to 0, which, why not? I'll do that. So if I make that as 0, I get x minus 5 plus 2i. I would add the complex number over to the other side, and we get 5 plus 2i equals x. So this is a 0. It's a solution, okay? So that's what it means by if it's a 0 of a polynomial. That is an answer. If I plug in 5 plus 2i into here, it does work. Okay? All right. Bless you. Use the remainder theorem to determine if the given number C is a 0 of the polynomial. So looking at this, here's what it's asking, okay? Just to be very clear on something, it bounces off of this. If I were to plug this in for x and simplify it, I get 0, okay? That this is gonna hit, or actually, it makes f of x or y 0, that's all. I almost said it was gonna hit the x-axis, but we know it doesn't, it's imaginary, it's not gonna hit the x-axis, okay? So instead of me plugging this into here and simplifying it, I'm going to use synthetic division to prove it, okay? And if it is a 0, what's going to happen is when I divide, the remainder is going to be 0, and that's what I want to look for, okay? Which implies it's the 0 of the polynomial. In other words, it's a solution to it. So let's go ahead and do some division. Okay. Oops. Wrong paper. There we go. So we have -1 plus I squared of 3. 1, 0, 0, and negative 8. Now the reason why I have two zeros, if you look at the polynomial, it has no x squared term and it has no x term. So I have to put those two zeros in place. Bring down the first term, put plus signs, and now we are off to the races. Okay? This, I don't know. If you're looking at it, it's like, really? Complex number, you're gonna multiply that through and add? Yeah, why not? Let's give it a shot. Looks fun. So 1 times this is just gonna be that. Okay? Now we're gonna add the column. We get the same. So negative 1 plus I squared 3. Here's our first, I don't know what to call it a speed bump, but now we're gonna multiply both of these, put the answer here. Okay, you know what? I think we better write this off to the side. So let's do that. So I'm gonna put this over here. So negative 1 plus I squared of 3 times negative 1 plus I squared of 3. It's okay. By the way, it's one of those things where I wouldn't expect you to do that in your head. Like especially when you have complex numbers, I would write it out so you don't avoid a mistake. Bless you. So negative 1's a 1. Negative 1 times this guy would just be minus I squared of 3. The middle term's the same way. And then the last term would be plus I squared times 3. Because I times I, square root of 3 times square root of 3. So we get 1 minus 2I square roots of 3. And then this would be a minus 3. Because the I squared is a negative 1. Numbers on the outside combined, so negative 2 minus 2I square root of 3. Okay, so that's what I'm going to put in the next spot. So minus 2 minus 2I square root of 3. Why did I write it in green? What the heck? Let's try that again. No. Yeah, no, I'm good. Okay. Now we're going to add them. Thank God it's 0. So here we go. Minus 2 minus 2I squared root of 3. Oh boy, we got to do this one more time. Man, who made this problem up? Okay, so here we go. Negative 1 plus I squared root of 3 times minus 2 minus 2I squared root of 3. Spoiler alert, it was me. I'm putting myself through this torture. So I'm going to multiply those two together. Now, here's the deal. I want the remainder to be 0, so I'm hoping my answer is 8 when I'm finished, right? So let's see if I designed the problem wisely. So we're going to multiply those together. We get a 2. Multiply the outside terms, plus 2I squared root of 3. In the middle, minus 2I squared root of 3. Last part, minus 2I squared, and then times 3. And I apologize, I know I'm going a little fast with that multiplying. I'm just trying to save a little bit of time. So the middle stuff cancels. I get 2. And this is now going to be a plus because an I squared is a negative, and there was a negative here. 2 times 3. And hey, that's 8. So I designed it pretty well. Put it this way, creating problems like this, it really does like hurt your brain after a while. It's like, I wanted to do this, so how can I work backwards for it to work like this? So this is a 0.
One of those are in Spanish.
One is in Spanish. So yeah, so is this an answer to this? Absolutely, okay? I guess we kind of did cube it in a way, didn't we? We kind of did in the same sense of it, but we did it by division. So there we go. Okay, so now the last thing we're going to talk about is what, factor theorem? Yep, that's it. Let's talk about the factor theorem. Okay. So let's go back to our division algorithm. equals x minus c times q of x plus r. And r is going to be a complex number. Okay. So we're going back to this guy, which I did erase it. I wish I had one more whiteboard that I could just have for some of this information. But you have it in your notes. I mean, so this is what we had before. The only difference is r is a complex number. Now just put this out there. 7 is a complex number because you could write it as what, 7 plus 0i? So just keep that in mind, that it doesn't just mean it has to have i's in it. It could just be real numbers because the real numbers are inside the complex. Okay, so there's our division algorithm, where c is a complex number. So let me rewrite that to show it. So x minus c times q of x plus r of c. If I can write correctly here. So some complex number. Okay? So here's the deal. If f of c is 0, then f of x equals x minus c times q of x. Okay, so let me stop for a quick moment to explain what that means. If something is a factor, are you going to have a remainder? No. So think about it this way. If I had 2 going into 6, goes in at 3 times, 0 remainder. Therefore, 2 times 3 gives me 6. I'm done. So the R of C, if it is a 0, right, if it actually is a solution, are you going to have a remainder anymore? No. That's what this is saying. Okay? So that's what we're going to be looking for in this case. So if it is a factor, if it does work, let me write this underneath it. So x minus c is a factor, then x minus c times q of x, you get c minus c times q of x, which gives you a 0, okay? So in other words, if it does work, we're going to get 0 at the very end. So putting a number example next to it makes it easier to interpret that. So let's go ahead and apply it. We're just about there, actually, if I remember correctly. Make sure I'm not missing a page. No, I'm not missing a page. We're good. Okay. That is a cool trick, not a cool trick, but like anytime you're doing mathematics and you have all of these different symbols and stuff like that, in my notebook I've done it. I put just a normal example next to it as a way to interpret and understand it. Because some of these definitions, it can get a little tricky. Okay, so here's the actual factor theorem written out for you. So let f of x be a polynomial. So first one, if f of c is 0, then x minus c is a factor of f of x. And then 2, if x minus c is a factor of f of x, then f of c is 0. Example. Use the factor theorem. Okay. To determine if -1 is a 0 of f of x equals 2x cubed plus 3x squared plus x. Okay, so that's what we're going to do. We're going to use the factor theorem to determine is -1 a 0. Okay? And if it is, we're going to do some more with it. We're actually going to find the rest of the zeros. Okay? So, let's go ahead and do that. So this is by part A. So we got -1. Now looking at this, am I missing anything? Yes. Do I have a constant term at all? I don't, so I gotta put a 0 in there. So it'll be a 2, a 3, a 1, and a 0. Bring the first term down, that doesn't change. Okay. And I tell you what, we haven't had no constant, so I'll put up here, this is the constant. Okay, because we're missing it. So that's a little bit different. Okay, now let's go through the process. So -1 times 2, -2. Add the column, we get 1. -1 times 1 is a -1. Add the column, I get 0. This is looking promising. -1 times 0 is 0. Add the 0, you get 0. All right, so guess what? It is a 0, meaning that -1 is an answer to this guy, right? So that's perfect. Now, here's the next part. So this is part A. I guess we'll put, can I squeeze A in there? We'll squeeze A in there. Okay, part B, okay, we're now going to solve the equation. 2x cubed plus 3x squared plus x equals 0. So now that we know that -1 is an answer, let's find the others, okay? Which, speaking of which, how many answers should this have? Three.
Yeah.
I get 2 markers in this hand. This is the best I got. 3. Okay, so I got 1 answer, right? Now, how do I find the other ones? Well, I could be here all day trying to divide by numbers to see what works, right? Let's be smart about it. What is this left over? So we start with an x cubed, so this must be an x squared, right? Okay, so my final answer over there was a 2x squared plus x. No constant term and no remainder. So that's what I have left over. Okay, so can we solve this for the rest of them? I think we can. I can factor an x out. So this is a 2x plus 1 equals 0. Apply the zero product property. So the first one would just be x is 0. The second one is 2x plus 1 equals 0. And then, well, that's what, -1/2. And I'll just put from before, what's equals -1. There's my solutions. So if you know one of your answers, if you divide it to get this polynomial at the end, which this actually has a, I don't know if you remember this. This is called a depressed polynomial. Don't like the name, but that's what it's called, okay? So, little extra fact. This is called a depressed polynomial. Okay? So yeah, just a little extra information. So find that polynomial, and then that's probably easier to solve for the rest of the solutions. And turns out, it is. It certainly is. All right, last example. Pinky promise, last example. Okay. So here's what we're going to do next to wrap things up. Okay. We're going to use these theorems to create a polynomial. So write a polynomial, f of x of degree 4 that has the zeros 1, -1, square root of 3, negative square root of 3. Okay? So I'm giving you the answers. Can you create the equation that gave you those answers? And the answer is, yeah, we can do that. But it's not going to be the most specific equation, and I'll tell you what that means afterwards. So how do we get these answers? Well, what gave us those? What about this? All those equations that I just wrote down. If I were to solve for x, does that give me all those zeros? It certainly does, right? Well, guess what I can do? If those are my answers, I can take each one of these and multiply them together. And then that's going to give me the original equation I started with. Does that kind of look familiar from last year, maybe? You had the answer, you're going to work your way backwards. Okay. Now I picked this, I think, pretty cleverly because these are opposites of each other, right? So it's going to make it easier to multiply this. So if I want to create this f of x, I'm going to multiply it by all of its factors. I'm going to be smart about how I multiply this, okay? I'm going to try to be smart. So I'm going to multiply these two together first, okay? I don't want to multiply these two together. They have nothing in common. Why don't we stick with something that does? So because they're the same, but the signs differ, is there going to be a middle term? No. So just multiply the outsides. So this is just x squared minus 1. Okay? So far so good? Now, let's do the same thing with the other two. Okay? I am right on the dot. We're going to do this. Same thing. They're the same factor. The signs are different. So then just multiply the outsides. So this is just x squared minus 1. And then the other one's going to be x minus 3. Nope, x squared, sorry, minus 3. Can't forget the exponent. Because what's the degree? 4. It's not going to be a 4 if I don't have it. So x times x gives me this, square root of 3 gives me this. Okay, now we multiply those together. So x to the 4th minus 3x squared minus an x squared plus a 3. I don't know why I did that. We don't need parentheses anymore. And then combine terms. So x to the 4th minus 4x squared plus 3. And there we go. Now, I want to be very clear on something. This is one possible answer. Okay, what are the other answers? What if I had a number out in front of here, like a 15 or a 4th or something? Wouldn't that still give me these zeros? Yes. So this is a more generic form of all the polynomials that has these zeros to it. Okay, so just keep that in mind. If you were working on a problem and you had like a number out in front, you're not wrong, because you can factor that number out and still solve these for the rest of the zeros. Questions? All righty, good job, guys.